So in the last video, we left off with this interesting question. I did an example where I didn't include a base for my log, and we were left wondering, like, what's that all about? So I wanted to lead with that in this example, and I wanted to spend a little bit of time talking to you all about what are called common bases. So I left a little space in the corner here. And the two common bases that we spend time with in this class, they're not the only common bases, but they're kind of the two that are most commonly accepted. So base 10, it's kind of clear why 10 would be a common base in our numerical system. Our numerical system is a base 10 system. So 10 is a really, really solid number. It is a number that's the foundation of the numbers that we write. So log base 10 is a really common base log that we use. And in fact, it is so common that we don't even bother writing the 10. Log base 10 is just written as log. So anytime that you just have log written with no underlying base, the understanding there is that you mean log base 10. The other common base is the number e. So e is a weird one. We haven't encountered it before, and we're going to say more about it later, but not this week. So e is what's called the natural exponent. For now, I'm just going to give you its decimal approximation. It's about 2.718. And it's an irrational number. It goes on forever, and I'm not going to say more about where it comes from. However, because it's a really prevalent number, especially when you're talking about things like natural exponential growth and decay, which we'll be doing a lot of, we never write log base e, because written like this, it looks kind of weird. It looks like somebody wrote the word loge funny, and then the e slipped down. So rather than writing log base e, we call it natural log, and we write it ln. If you pull out a calculator and you kind of examine what the options are when it comes to logarithms, about 95% of calculators don't have a button for log that has a base on it. You'll see two buttons for log on most calculators. Not all of them, but most of them. You'll see the log button, which is just log without a base, aka log base 10. And then you'll see the ln button, which is log base e, and that's also known as the natural logarithm. So I'm going to write that here just so that you have that for reference, the natural logarithm. Okay, and the reason that it's called the natural logarithm is that it's the logarithm whose base is the natural exponent. So all of this has been building up to the idea that we can solve equations using the properties that we're starting to observe between logarithms and exponentials. So I thought that we'd do some examples of solving exponential equations. So I have some on this page, and then I actually have some more on the next page. So the first example that I wanted to spend a little bit of time on is the one where you actually don't need logarithms to solve. I sometimes call these simple exponential equations. You'll sometimes hear me refer to them as really nice ones because you don't need to get messy with logarithms or anything like this. And the thing that makes them nice or simpler is that both of the bases are powers of the same number. Are, and I'm going to put in quotes here, easy powers of the same number. And of course, in this example, that's 2. Okay? So 2 to the power x plus 3 is equal to 4. I can write that as 2 to the power x plus 3 is equal to 2 squared. And whether you want to make a big to-do about it or not, since exponential functions are one-to-one, if two powers of 2 are equal, the powers must be equal. So x plus 3 must be equal to 2, so x is -1. Okay, so the solution to this equation is -1. Okay. All right, let's look at number B. So B is very, very similar. We have 27 to the power 3 minus x is equal to 9 to the power x plus 4. And I'm going to write this here again. Both bases are, quote, easy powers of the same number. In this case, it's 3. So 27 is 3 cubed. 9 is 3 squared. And then from there, you remember that when you have a power raised to another power, the powers multiply. So what we end up with is 3 to the power 9 minus 3x is equal to 3 to the power 2x plus 8. So since we have two different powers of 3 equal to each other, we have 9 minus 3x is equal to 2x plus 8. And then from here we have a linear equation which we can solve. So we can add 3x to both sides, subtract 8 from both sides, and sorry about that. And so we have 1 is equal to 5x. So x is 1/5. So the solution to this equation is 1/5. All right, so that's all very well and good when the bases are kind of easy powers of the same number. But if we move on to something like what we see in number 2, where we have something base 3 on one side and 5 on the other. Now, you could actually use logarithms to write 5 as a power of 3. And I encourage you to do that. But certainly you will agree with me that 5 and 3 are not easy powers of the same thing. They're both prime numbers. Neither one of them is really a power of anything nice except themselves. So this approach of rewriting everything to be a power of the same thing and then going from there, that's not going to work here. The big idea in problems like this is that if two numbers are equal to each other, if two values are the same, then their logs are equal to each other too. And vice versa. So this comes straight out of the fact that logs and exponentials are both one-to-one functions. So we can be assured that if we want these two things to be equal, 3 to the power x minus 2 and 5, we know that it's the same as wanting their logs to be equal. So that's what I'm going to do to start. I'm going to take the log of both sides. Notice I'm using a common log, and in this particular example, I'm using base 10. But it doesn't matter what base you use. As long as you use one of the common logs, you're going to get the same thing no matter what. And on the next page, we'll actually look at some examples where, oh, sure enough, we can do it base 10 or base E. We get the same thing in the end. Okay, properties of log central. So we have log of 3 to the power x minus 2. So we have this exponent here. So by properties of logarithms, that x minus 2 pops out. Now, here's the thing. Log 3 is a constant. And I'm going to write that here to sort of remind us. Log 3 and log 5 are constants. In much the same way that like 2 and -7 would be constants. So we want to solve for x. So we want to get x by itself. And that log 3 is going to get distributed through. So we have x log 3 minus 2 log 3 is equal to log 5. Our goal is to get x by itself. So we're going to subtract or rather, excuse me, add 2 log 3 to both sides. And then we want to get rid of that log 3 on the left, so we're going to divide both sides by log 3. And remember, log 3 is a constant. So the solution here is log 5 plus 2 log 3 over log 3. Please be careful. You cannot cancel out the log 3's here because only one of the terms in the numerator is divisible by log 3. So you might be looking in this and you might be thinking, ugh, that's kind of messy. Well, the good news is that if a problem asks you for a rounded version of this, so I'm going to pick a different color, let's say blue, you can actually punch this into a calculator. Because you're using a common log, you're using a logarithm that your calculator knows how to work. So on top you have log 5 plus 2 log 3. So we can punch that in, log 5 plus 2 log 3, and then we're dividing that by log 3. And so what we get here is 3.465. This is the rounded value, rounded answer. And if you are paying attention in your homework, sometimes you'll be asked to just give the exact value, and sometimes you'll be asked to give a rounded value, and then it'll give you a number of decimal places. Okay, so now let's move on to another few examples. So I'm going to move to the next page here, and as you know, I'm having to re-record here. So I'm going to start with this example. In no small part, because this is very similar. This is going to be very similar to the one that we just did. And in no small part, I want to do this so that we get kind of a little bit more comfortable with what we're trying to achieve here. So I have several examples here, and all of this is just working to get comfortable with the notion of using common logs and a little bit of properties of logarithms to solve exponential equations. In the first example, we have 5 to the power x plus 7 is equal to 2. This is very, very similar to the one that we just solved, but the reason I'm showing it to you is because at first, I want to look at solving this equation using log, and then I want to solve it using natural log to show you that you get the same thing either way. So I'm going to remind you here again, since it was on the previous page, that if A is equal to B, then log A is equal to log B. And when we're at it, we might as well say natural log A is equal to natural log B. So let's go ahead and take log of both sides. Okay. So we have log of 5 to the power x plus 7 is equal to log 2. By properties of logarithms, the x plus 7 pops out here. So we have x plus 7 times the log of 5 is equal to the log of 2. And I didn't write this in the last example, so I want to just do it here. Log 5 and log 2 are constants. They're constants in much the same way that like -7 or 14 might be constants. They are just numbers. Now, are they rational? No. Do they have a terminating decimal representation that's nice or repeating? No. So we're not going to write them using decimals, but we're going to treat them the same way as we would any other constant. So the first thing we're going to do is we're going to distribute the log 5 through. There we are. And then we want to get x by itself. So we're going to subtract 7 log 5 from both sides. And then we're going to divide both sides by log 5 to get x by itself on one side. And now that x is by itself, we have the solution. So the solution to this equation is log 2 minus 7 log 5 over log 5. Now, that is the precise value of the solution of this equation. But say for whatever reason you wanted a sense, what kind of number is this? So you can, and you will encounter this in your homework, you can get a rounded value here. So let's see what we get when we punch it into our calculator. So we have log 2 minus 7 times log 5. And then we're dividing this by the log of 5. So this is approximately negative 6.5. I'm just going to round it to 2 decimal places this time. It's approximately negative 6.57. Now, in the bottom part of this page, I wanted to show you that it doesn't matter whether you're using log, like log base 10, or natural log, like log base e. So I'm going to do the exact same problem, but rather than using base 10, I'm going to use base e. Fairly soon after the whole base e maybe weirdness wears off, many of you will notice that you will start favoring natural log to log because it's a little less writing, it's a little more compact. Again, by properties of logarithms, the x plus 7 pops out. Again, natural log of 2 and natural log of 5 are constants. So we can treat them in much the same way that we would treat any other constants. So we're going to distribute on the left. And now we'll subtract 7 log 5 from both sides. And finally, to get x alone, we'll divide both sides by the natural log of 5. Now you'll notice that when I'm talking, I frequently slip up and I actually call natural log log. In no small part, this is because it's the log that really ends up being preferred. And so you'll hear more and more when people say log, what they're actually talking about is natural log. All right, so let's write this here. The solution to this equation is the natural log of 2 minus 7 natural log of 5 over the natural log of 5. Again, we don't want to get carried away. You can't reduce that natural log of 5 because only one piece of the numerator is divisible by it. But let's punch this in to make sure we get the same number. So I have the natural log of 2 minus 7 times the natural log of 2 minus 7 times the natural log of 5, and then divided by the natural log of 5. And sure enough, we get the same number. And again, I'm just going to round it to 2 decimal places, but it's the same number, negative 6.57. So it really does simply become a matter of ease. And you'll notice very frequently that using natural log is a little bit cleaner than using base 10 log because it's just a little bit less writing. Okay, let's look at another example. So in this example, you'll notice that the unknown is located on both sides of the equation. That doesn't deter us at first. We use our same basic idea. If two things are equal to each other, then their logs must also be equal to each other. So we're going to go ahead and take log of both sides. And I'm just going to take natural log because I already know from my previous example, it's a little bit less writing. It's a little bit less work. So again, by the properties of logarithms, the exponent pops out. So I end up with x minus 5 times the natural log of 3 is equal to 2x plus 3 times the natural log of 2. And remember, the goal is to get x by itself on one side. So what I'm going to say here is we're going to group all of the terms with x in them to one side. Okay, so here we go. To do that, we're first going to distribute. So we have x log 3 minus 5 log 3 is equal to 2x log 2 plus 3 log 2. Okay. And I'm just going to underline them. Like, here are the terms that have x's in them. So I want to put them together on one side and put everything else to the other side. How you do this doesn't really matter. So I'm going to go ahead and subtract 2x log 2 from both sides, which will move all of my x terms to the left. And then I'll add my 5 log 3 to the other side to move everything that doesn't have x in it to the right. So here goes. Okay, and now you see the benefit of having moved everything with x's in them to one side. We can factor x out from the left. That was the plan here. So we have x times the natural log of 3 minus 2 natural log of 2 is equal to 3 log 2 plus 5 log 3. And finally, to get x by itself, we'll divide both sides by the thing that x is being multiplied by here. So the solution is 3 log 2 plus 5 log 3 all over log 3 minus 2 log 2. Now, what I want to do is I'm going to give you the rounded answer here, the rounded value, but I really encourage you to punch this into a calculator yourselves to make sure that you get the same thing. All right, so here we go. On top we have 3 log 2. So we're going to punch that in, 3 log 2 plus 5 log 3. And then on the bottom, we have natural log of 3 minus 2 log 2. So this is approximately negative 26.322. So what I encourage you to do is punch this into a calculator and make sure you get the same value. If you don't get the same value, chances are there's a parentheses issue or something like this, but make sure to check in with me or with Irina if you're not getting that same value. The last thing that I'm going to say in this video is something that I'm going to pick up in the next video, which is the idea that, yes, we are now solving exponential equations using this relationship between exponentials and logarithms and properties of logarithms, and all of that is very well and good. But we should never forget that we still have other techniques for solving equations. You know, we have dividing both sides by a constant, we have factoring, we have distributing. All of those things still hold true. So I want to show you a baby example of an equation that uses kind of old techniques in addition to new ones. And then in our next video, we'll look at some more interesting examples, which will be taken straight from your homework. So say that you have something like this. 3.25 times 1.07 to the power 2x is equal to 8. Okay? So on its face, this problem looks significantly more intimidating. There's decimals and oh my god. But as soon as you dig a little deeper, you realize this is just an exponential equation. You've got an exponential on the left, and so you can do the whole log thing. But before you do that, you'll notice that your exponential is being multiplied by 3.25. And so you say, oh, well, I know how to get rid of that 3.25. I can divide both sides by it. Okay, so on the left, we have 1.07 to the power 2x. On the right, we have 8 over 3.25. So, I'm going to go ahead and keep it as 8 over 3.25, simply because if I divide it, I end up with a pretty big decimal, and I don't want to deal with that. So this is a straight up exponential equation. So I'm going to say if these guys are equal, then so are their logs. So the log of 1.07 to the power 2x is equal to the log of 8 over 3.25. Notice that I'm using natural log for ease of writing. Even though I'm calling it log, it's perfectly fine to use natural log. By properties of logarithms, the 2x pops out. And then since I want x by itself, I'm going to divide off the 2 and the natural log of 1.07. So that is the official precise answer. That is the official precise solution to this equation. But let's say that in this problem, and this is actually a problem very similar to one that you have in homework, you're asked to approximate it, say to 3 decimal places. So same thing, I'm going to do it, and I encourage you to do it along with me and make sure that you get the same thing. So on top we have the natural log of 8 over 3.25, and then we're dividing it by two natural log of 1.07. And so what we're getting here is approximately negative 8.710. So this, of course, is the rounded value. And unless we're asked specifically, explicitly in the problem to give the rounded value of an expression or the rounded solution to an equation, we always give the precise answer. Because anytime that you round, you're admitting rounding error. In the next video, we're going to look at some examples of solving exponential equations that end up using even more techniques that we've learned before, specifically techniques surrounding factoring and quadratic equations. So that's it for this video. Stay tuned for the last video on exponential equations.